be from the correlogram itself. Okay, so we are having correlogram as one more attribute, okay, of a time series, which is to be studied, is to be also discussed. Okay, and you get now some more insight into the time series data set itself. Okay, so I will be now doing some certain exercises which are okay, on the software, eView software. Okay, and we can use that for getting okay some of these okay features of time series, okay, to be understand more widely itself. Okay, so let me just open. So I have some simulated data set with me, okay, and they represent some okay, aspects of these stationary and non-stationary time series, etc. Okay, so let me just hook up some of these data set, okay, for you. So what I want to have is okay. I'm just trying to generate certain data set, okay, 1,000 such data. Okay, that's what I want to generate. So I have time point starting from 1 to 1,000. Okay, so I'm having that, and what I've been doing is okay. I'm just generating my okay some another series. Okay, let me call it as series 1. Okay, and that happens to be a random variable. Okay. Okay, so what I'm doing is I'm in my Excel, okay, I'm just simulating certain data set. I'm generating certain normally distributed variable. So I'm using a function norm, okay, dot inv, and okay, so I'm generating a random variable which is following a 0 mean and 10 as the standard deviation. A 0 mean and 10 standard deviation, different number of random variable which is distributed normally itself. Okay, so I get something like 5.95. Okay, and I'm just going to drag it. So I have okay some of these random variables which are being generated itself. Okay, so when I look upon this kind of series, okay, so I have a simulated series. Okay, and let me using this simulated series. Okay, let me just okay, have time series plot of this data set, okay, and the other graph, okay, so as to understand what is the basic nature of this kind of data. I'm foretelling, I'm preparing it, okay, in advance, so I know what is the basic nature of this data set. But okay, most of the time you have the data, and then you need to understand whether okay this kind of a data set is useful, okay, or what kind of random variable or the stochastic process has been behind okay this kind of a data set itself. Okay, so I know from by looking at a graph, I know beforehand, but in your real life, okay, you only have data set okay to be used for okay understanding or making inferences about the stochastic process. Okay, so I'm just copying this entire data and just pasting it, okay, or bringing it in a file. Okay, so what I have done is okay, I have just taken the data set and I have okay, imported in eViews file, and this is the data set which I've been having. Okay, so the same data set starting from the observation number 1 to observation number 1,000, I'm able to successfully import my data set in eViews. Okay, so now I have this kind of a data. Now, to be able to understand what is the nature of this data set itself, okay. So of course, okay, I'm going to talk about all the three aspect which I said in the presentation, okay, that we can look at, okay, while analyzing a time series data set. So I'll look at the time series plot. So I prepare a graph, I look at the correlogram, and I'll go for the stationarity itself. Okay, so let me just focus on that aspect. So while firstly, okay, looking at the graph, so I go to view and going for a graph and a line graph. Okay, so I'm interested in that. Okay, and this is the series which I have been having here. Okay, so by looking at the graph itself, and of course, okay, I prepared it myself. Okay, we generated it ourselves itself. Okay, so we know the basic attribute itself. So it is for this entire series, which is a stationary series. Okay, you find it that, okay, these are all hovering around the value 0. So mean value happens to be 0, and okay, they are not too much deviation which you have been observing it here. So the entire data set is lying between, okay, two such barriers, upper and the lower ones itself. Okay, so it doesn't have any drift, it doesn't have any trend. Okay, and you are really looking at the data set which looks to be a stationary data set itself. Okay, so the first aspect of analyzing this kind of a time series is you plotted it on a time graph, okay, a timeline, okay, and you have generated this uh, graph, okay, which is your time series plot itself. Okay, that's first way of analysis. The golden rule of data analysis says, okay, when you go and start a data analysis, always plot your data. Okay, have a feel of the data itself. Okay, only when you have okay, taken a glimpse at the data itself, okay, even taken a feel of the data set, only then you go ahead, okay, and go for the data analysis. Okay, it is a further steps. Okay, so three rules. Okay, make a graph, make a graph, make a graph. Okay, that's a first, okay, significant step in the use of the data analysis itself. So you have plotted the graph itself, okay, and now you can identify at least some of the basic nature of the data set itself. Okay, I've also generated certain more simulated data set as well, okay, at the back, and we can also use it, okay, for our purpose. Okay, for let me just copy that as well, and okay, and go for eView, so as to just compare this kind of a data set with some of the data set itself. Okay, so I have this series one, okay, as my simulated data set, and I have also have, okay, some more data set. Let's take it something like this. Okay. These are all simulated data set. Okay, so this will be giving you different attributes. Okay, so you have now this random walk model. Okay, and you also have something which is your uh, stationary variable. So this is a graph of a stationary data set. Okay, this is a graph of a random walk model as well. Some of okay of the scholars, okay, have this kind of understanding that random walk is a stationary process. Okay, but random walk is not a stationary process. Okay, you can also see it. Okay, can anyone make out, okay, which is the random walk, is a stationary or non-stationary?
It is non-stationary, sir.
Okay. Random walk is non-stationary. You are having some sort of, okay, jumps in the mean value, the conditional mean values here itself, okay, which you are not having it here. Okay, so there are for every, okay, for any length of okay, certain number of days or time span, if you compute the average will come up as same throughout itself. But that averaging is not been there itself. Okay, so please do, okay, also appreciate the fact that generally random walk models are, okay, or rather random walk model, okay, conceptually is a non-stationary process. Okay, so you don't work on the non-stationary series, you have been working only on the stationary series itself. Okay, so first aspect of data time series data analysis was looking at a graph. Okay, and so wherein you do get some insight from the data set itself. Okay, now, second aspect was a correlogram. Okay, I will be coming shortly to that as well. Okay, and the third aspect was also the stationarity as well. Now, okay, I will be directly been jumping towards okay the stationarity itself, and let me now formally define what exactly is the stationarity itself. Okay. Okay, so I talked about that stationarity as a concept, okay, has two things, okay. And there are two levels of understanding of stationarity. One is the weak stationarity, another one is the strong stationarity itself. The weak stationarity talks about only the two moments, okay, mean and the variance, okay, or rather covariance itself. So constant mean, a time series is said to be weakly stationary if it has a constant mean. The mean remains the same. Constant variance, the variance also remains the same, and covariance, okay, function is dependent upon the time difference, okay, between the values of the variable itself. Okay, it's not dependent upon, it may be dependent upon time lag, but it must not be dependent upon the time point. So that's what is the third aspect. Okay, and okay, if or in very simple word, if the mean is constant, covariance, sorry, variance is also constant, and covariance is also constant. It's also a number which is not dependent upon t. It is a number which is a constant. Okay, that surely is a weakly stationary series itself. Okay, so mean is a finite number and it doesn't have a subscript t. Okay, so expectation is, or the mean value is constant number. The variance value does not have, and again, any subscript t, and the covariance is also does not have any subscript t. Okay, so it's independent of the time zone itself. Okay, however, to compute a covariance, obviously you need, okay, this series with its own lag. And what is the lag which you will be taking? That's a lag happens to be k. Okay, so it might be dependent upon k, but it must not be dependent upon t. Okay, so all the right hand side things, okay, must not have a subscript t attached to it. Okay, which basically means, okay, that they are all constant itself. If these three conditions are satisfied, you talk about the series as a weakly stationary series. And if you talk about strong form of stationarity itself, then the mean should remain constant, variance should remain constant, skewness should remain constant, kurtosis should remain constant. Okay, all moments must remain constant itself. That means there should be an exact replica every time. Okay, so which in other words, in our okay verbal understanding means, okay, which I also talked about in the previous session, that if you are rolling a dice to generate the first data point, the second data point must also be generated by exactly the same random experiment, which is again the rolling of a dice itself. So for the first data set is coming from rolling of a dice, the second data set is also coming from rolling of a dice, the third data set is also coming from the rolling of a dice, and so on. All data set is coming from the same random experiment, which is the rolling of the dice itself. Okay, so their means are the same, their variances are same, their covariances are the same, their skewness is the same, their kurtosis is the same, everything exactly is the same itself. Okay, while in these weak form, okay, we simply content ourselves with the two moments, which is mean and the variance itself. So the mean remains the same, the variance remains the same, we are happy with that. Okay, we do not, okay, and of course the covariance as well. Okay, so we are not bothered about okay, skewness, kurtosis, or any other higher moment itself. Okay, so we still work for all practical purposes with the weak form of the stationarity itself. Okay, now to test this stationarity itself, okay, we are talking about, okay, certain tests, statistical test, and how does, okay, but this stationarity is getting violated. I already talked about in the previous session that it's either the okay, a trend, deterministic trend, or stochastic trend, which might be resulting into, okay, non-stationary series, and also, okay, the structural breaks, okay, can also make your series non-stationary as well. Okay, so when you have non-stationarity coming from deterministic trend, okay, you detrend the series. When your non-stationarity comes from stochastic trend, you difference the series. And when the non-stationarity is due to the structural breaks, okay, you go for the adjustment of the structural breaks by use of the dummy variables itself. Okay, so detrending, differencing, and making an adjustment for the structural breaks, okay, is the common techniques, okay, which has been used to make a non-stationary series into a stationary series. Okay, and you should always be running a regression or doing your data analysis okay, on uh, you must also be doing okay your analysis only on the stationary data set or not on the non-stationary data set. Okay, so talked about that as well. We talked about the structural breaks, okay, which is also results into non-stationarity as well. Okay. Now, looking at okay the graphical version, which I talked about in the yesterday's sessions. Okay, we do have statistical tests. Okay, which can give you statistical evidences with the presence or absence of the stationarity itself. So there are a couple of tests. Okay, Dickey-Fuller test, augmented Dickey-Fuller test, uh, the ERS test or Dickey-Fuller GLS test, okay, Phillips-Perron test, KPSS test. Okay, in these tests, okay, you have certain improvements in these tests itself. Okay, these are some of the widely used tests for the checking of the stationarity itself. Okay. So Dickey-Fuller test, okay, had an assumption at the back of it that the error terms are uncorrelated, okay, that there is no autocorrelation in the error terms. But as I talked about, okay, in almost more than 90% cases, okay, when you have been dealing with the time series data set, the error terms are okay suffer from the problem of serial correlation. So the error terms are suffering from the problem of serial correlation. Okay, then this kind of a test is not really so much useful a test. Okay, so there is an augmented Dickey-Fuller test which takes the note of the assumption that error terms are correlated itself. While the third test, which is a Phillips-Perron test, okay, assumes that there is a correction for autocorrelation and there is a correction for heteroskedasticity as well. So Phillips-Perron test is generally been okay, accepted okay, for checking for the stationarity itself, because in most of these cases, your data set do suffers from the problem of autocorrelation and as well as heteroskedasticity. These are the common nature of the data set time series, most economic and financial data set, that it suffers from both these problems, and hence okay Phillips-Perron test is generally okay, accepted for the testing of the stationarity itself. Okay. So how you go for the unit root testing itself? Okay, so we can do that again in your reviews itself. Now I know for sure that this is a series which is a stationary series, and I am also sure that this is a series which is a non-stationary series itself. Okay, so I want to have a look at okay. I commented on that based on looking at a graph itself, but just by looking at a graph and you writing it in your research papers, in your thesis work, okay, that this is a stationary and this one is non-stationary, will not go well. Okay, so you need to provide a statistical testing for this attribute of the time series as well. Okay, so for this, okay, I want to go for the checking for stationarity. I go for view. Okay, I go for unit root test. Okay, so I have three options here. Okay, depending upon the version of EQs which you have, you might have okay, just two options or only one option might also be there. The standard unit root test, okay, which does not take into consideration any structural breaks in the data set. Breakpoint unit root test, okay, which takes a series which is suffering from the structural break. Okay, so if you have a structural break in your data set, then you can go opt for the breakpoint unit root testing itself. Okay, and if your data set is also having exhibiting some sort of a seasonality, okay, then you need to also go for the seasonal unit root test itself. Okay. So here I don't have any seasonality, okay, but yes, of course, in some of the economic time series, you will be having a seasonality as well. For example, for money supply, you have a busy season and the slack season. So you do classify your data set into certain seasons, and okay, as a result of that, okay, you need to go for the seasonal unit root testing as well. Okay. So here I go for the standard unit root test. Okay. I went ahead. The default is the augmented decay Fuller. Okay, so if you do not think that there is a heteroskedasticity in the data set, ADF will suffice. But if you say that there is a heteroskedasticity, then you can go for the Phillips-Perron test as well. Okay. When you have a small sample, these are all large sample tests. Okay, I have taken 1,000 as the sample size, but again you need to go for more as well. So when you have okay large sample, okay, then these ADF, Phillips-Perron, okay, they are sufficient. But if you have a small sample data set, then you need to go for the GLS based or ERS based test, okay, which has relatively more power as well. Okay. So I can go for the Phillips-Perron, I can go for the augmented decay Fuller, okay, for testing my unit root itself. Okay. So I go for let's go for the Phillips-Perron. But the data set which I have, I know it's a simulated data set. Okay, it will not have a problem of autocorrelation, and also it will not have a problem of heteroskedasticity as well. Okay? But if you are not sure about it, okay, of course you have the Phillips-Perron, okay, to be used at the first stage itself. Okay? So I go for Phillips-Perron test, okay, and let me come back to these stuff one by one. So I'm just testing it at the level, and I simply press OK, and I generated my test results itself. Okay? Now, how to make sense of these test results? Now, the null hypothesis of all these tests, okay, except a test which is referred as your KP-KSS test. Okay, in all these tests, your null hypothesis is that the series has a unit root, which other word also means that series is a non-stationary series. So my null hypothesis is series is non-stationary. Okay. So if you are rejecting this particular hypothesis, that means then the series is a stationary series, and you can go ahead and run a regression on the stationary series. If the series comes up as a non-stationary series, okay, then in that case you can't work with a non-stationary series. Okay, and you need to convert them into stationary series and run a regression. Remember, okay, with only one caveat, okay, if you are working with a non-stationary series and these series in combination happens to be co-integrated, then in that case you can go for the running a regression even on the non-stationary series, okay, by referring it to the vector error correction model and power models as well. Okay, okay, so I went ahead with that itself. Okay, so my null hypothesis is that series 1, which is the name of the series, has a unit root, which in other word means that series is non-stationary. If you look at the p-value, the p-value is 0.000, which is less than your cutoff value. Okay, you can have a 1% cutoff or a 5% cutoff. So at a cutoff level of 5%, p-value is less than 0.05. Okay, so null is to be rejected. So you reject the null. The series has a unit root, which in other word means series is a non-stationary series. This null is getting rejected. Okay, so that means the series is a stationary series. Series 1, which is the name of the series, is a stationary series by virtue of this testing procedure itself. Okay? Which was also been evident from the graph as well. Okay, we were saying it beforehand that my graph shows that it's a stationary series, and that's also been supported by the test results as well, that the series is a stationary series itself. Okay. Okay, so how can we come to know about whether your data set do suffers from heteroskedasticity or not itself? Okay. Okay, in that case, okay, your detection of heteroskedasticity is another aspect, okay, and I didn't went into that itself, but as a part of cross-sectional data analysis, okay, we talk about these assumptions, okay, 1 to 10, and the presence of homoscedasticity or heteroskedasticity, okay, is also which is there even with the cross-sectional data set, okay, and that could also be there with the time series data set as well. Okay? So whether okay your data suffers from heteroskedasticity or not, okay, so there's a separate section on that. So there you can go for checking for okay whether there is a heteroskedasticity. So Park test, White test, okay, Glitzer test, there are some of the tests, okay, Arch LM tests. These are some of the tests which you can use it. There are graphical ways of detection of heteroskedasticity, okay, whether your data set do suffers from the heteroskedasticity. Okay. So there are multiple ways of okay, detection of heteroskedasticity, multiple ways of correction for heteroskedasticity as well. Okay. So there are ways and procedures available on that. I'm not getting into it because that will be okay too much of a digression. But yes, okay, your standard textbooks on okay any regression analysis itself talks about those aspects itself, okay, in greater detail. So you can refer to those sections on the detection and correction for heteroskedasticity. Okay, so this is what I was having at the beginning. Okay, and we know that by looking at a graph as well, we were able to make out that the series, this happens to be a stationary series, and by checking for the unit root test, okay, we have also rejected the null hypothesis, and, which says the series is a non-stationary series, which is getting rejected. So my series is a stationary series itself. Okay. So another test, which is a KPSS test, okay, you have to also keep in mind that all except the KPSS test, okay, they have the same null hypothesis that the series is a non-stationary. In the case of KPSS test, okay, the null hypothesis is that the series is a stationary series. Okay, so here in the case of KPSS test, you look for the okay, acceptance of the null hypothesis, while in the case of okay, other tests, ADF, Philip Perron, ERS, and other, okay, you look for the rejection of the null hypothesis. Okay. So in the case of KPSS as well, if we test for that, okay, your p-value is sorry, this is your LM statistics, okay, and these are the cutoff values itself. So you have at 5% level, the cutoff value is 0.46. The statistics arrived at is 0.089. This is less than this cutoff statistics. Okay, so statistics calculated and statistics tabulated, these are been provided to you. So the first one, okay, is 0.089 is the statistics calculated, while these are the three which is tabulated itself. So at 5% benchmark, okay, or at even at 1% benchmark or a 10% benchmark, but let's stick to benchmark of 5%. Okay, significance level of 5%. So at a significance level of 5%, the benchmark is 0.46. Your computed value is 0.089. Okay, so this falls into your statistics computed falls into an acceptance region, and you accept the null hypothesis. And the null hypothesis is that your series is a stationary series itself. Okay. That's the one aspect. Okay, testing for okay this kind of a series, which is already you know in advance is a stationary series. Now this is a series which is a non-stationary series. Okay, so I need to again go for the statistical test here as well. I go to the standard unit root tests. Okay, and I go for let's go for the Philip Perron to begin with. Okay, and I press OK. The p-value is 0.9265, which is greater than 0.05. Okay, so this means that okay you are accepting the null. Okay, and the acceptance of the null means that your series happens to exhibit a unit root. Okay, or the series is a non-stationary series. So you are accepting a null hypothesis here as well, and the series happens to be a non-stationary series. So I'm able to confirm it statistically as well. So it's not always the graph. It's also the test is also able to confirm you that what kind of series okay you have been working with. Okay, so obviously the random walk series which I picked up, this is again a simulated series, is happens to be a non-stationary series. Okay. So you can pick up your own data set for GDP, FII flows, or motivation levels, okay, and stuff like that, whichever happens to be a time series data set. You can go and check for the stationarity. Okay? So stationarity is also an important aspect. Okay, before you jump to making a data analysis of a time series data set. Okay? Now, in both these testing procedure, what I have actually done is okay, I have accepted all the default itself. I've not went for the change in the uh, in my default setting. Okay, but yes, okay, you should be slightly careful while testing for these kinds of attribute itself. Now, if you look at the graph here, okay, and let me also have a look at the graph here as well. Okay. In this case, I know it beforehand that there is there's no trend in the data set. So there is no trending upward or downward movement. There's no trend which you have been observing in this kind of a data set itself. Okay. So I didn't opt it for those kinds of variation in my testing as procedure as well. But here in this case, you can clearly see that this is okay having some sort of a trend itself. It's moving upward. Okay, so there is some trending which has been there, and your non-stationarity should also be able to capture this kind of trending behavior as well. Okay, so when you go for testing procedure, you also need to identify these aspects, and you need to use it in your testing procedure itself. Okay, so what I'm basically talking about, let me come back to it. Okay, so when I go for view and the unit root test, I have these three options with me: intercept, trend and intercept, and none. Okay, so should I should be choosing the trend? Should I be choosing the intercept? Should I be choosing none? Okay, which of the option is what I should be choosing? That's a pretty important decision as well. Okay, differencing, the question on differencing arises when you have a non-stationary series in your hand and you want to see that by some alteration, okay, this is sort of a post hoc analysis itself, okay, with some alteration or of what kind of alteration I can make my series, okay, as a stationary series. Okay, so for that purpose you can go for this aspect, but before you go for that, for even testing itself as a primary goal, okay, you need to choose from these three options itself. Okay, now to choose from that, okay, again your graphical understanding of a data set will be quite useful in that case. Okay, I have a series here, okay, that doesn't show any kind of a trending behavior, either upward or downward, but it doesn't show you any kind of trend itself. Okay, so I should not be opting for this trend option. Okay, again in this case, okay, the series which I generated, and that I generated in using Excel, and my Excel, okay, already picked up that my mean value is 0. So all these observations which I have used it for testing procedure, they're all hovering around the value 0 itself. Okay, so they are all must be hovering around the value 0. So if it is a non-zero number, okay, then I need to opt for intercept. Okay, so if you have any deterministic trend, remember only the deterministic trend, not the stochastic trend. If you see any deterministic trend, you need to opt for trend and intercept option. If you see that these observations are going to be hovering around a value which is different from 0, you need to go for the selection of intercept. And if you think, okay, there is no trend in this data set and all these observations are hovering around the value 0, okay, then you need to opt for the choice which is done itself. Okay, as I know that when I tested for this series, I know it beforehand that it is hovering around the value 0, and they are all drawn independently, so they do not suffer from any autocorrelations as well. Okay, and this data set, okay, does not exhibit any sort of a trend as well. Okay, so ideally speaking, for testing this series, I should be opting for the none as my option in the test equation itself. Okay, so test equation for testing, same thing. Okay, whether it's a flip Peron, whether it's a ADF, whether it's a GLS test, whether and some of these tests itself. Okay, you need to have this choice between intercept, trend, and none. Okay, in this kind of a series, because I know beforehand, okay, a correct option would have been none. Okay, and I should have
And
chosen
can we
that.
use trend and intercept both?
Sorry, I didn't get you.
So when we can use intercept and uh, trend or like together, in which case we can use that
Trend will
option.
not come it independently. So trend and intercept is always the case. Okay, so if I go to view and go for unit root, okay, trend is coupled with the intercept. Okay, but is there any trend or not? You need to also make a selection for that as well. Okay, so this is trend and intercept okay, that you will only be choosing when you see that your data set do exhibit trending behavior itself. Okay, your data set does not have a trending behavior, okay, then you must not select for trend and intercept. Okay. For example, in this series, the series here, you know that there is some sort of an upward trend which you have been observing. So in this testing procedure, you should opt for trend. Okay.
Okay.
So that's why, okay, I picked up two examples and contrasting them, okay, one another itself. Okay. While in this kind of a data set, okay, they were all hovering around the value 0 as well. Okay, so even there is no intercept, there should not be any intercept in the equation as well. Okay, so correct testing procedure for this kind of a series would have been by choosing the option which is none. Okay, so I select for none. I'm going for the Phillips Perron test itself. Okay, I'm going for this itself. Okay, and I should be using this for my reporting purposes, whether my series is a stationary series or a non-stationary series itself. Okay? So it doesn't have any intercept value. If you look at the test equation, okay, this section gives you the test equation itself. Okay, if you look at the series itself, okay, there is no intercept. Okay, it doesn't have any intercept itself, and the p-value which you have been getting is less than 0.05. That means you need to reject the null hypothesis, and the null hypothesis says that series is a non-stationary series, which is getting rejected. That means your series happens to be a stationary series itself. Okay, that's for the testing for this kind of a series. Let's take this one. Okay, you know that this series is okay, more or less okay, secularly trending upward. There's an upward trend which has been here. Okay, so what should you do? Okay, when you go for the testing for the unit root itself, okay? You should recognize this aspect in your testing procedure as well. Okay, so you go to view, you go to the unit root test, standard unit root tests, okay, and you should opt for trend and intercept. Okay, recognizing the fact that okay, this series happens to exhibit okay some sort of a deterministic trend behavior. Okay? So I went for the Phillips Perron trend and intercept and pressed OK. Okay. Now, even if you have chosen that itself, okay, it doesn't mean okay, that you can straightforward and again go here and starting making sense to that itself. Okay. Now, because you have opted for the trend and intercept, okay, and while this series you have not opted for, you opted for none. Okay, what is the difference you will be finding in this case? Okay, so remember here the name of the series is series 1, so there is a series 1 minus 1. That means there's a lag of 1. Here the name of the series was RWWD, okay, and there's the RWWD minus 1. Okay, so that aspect is the same in both these okay, version itself, except okay that the name of the series has changed. But because here you opted for trend and intercept, so there is a trend component coming in here, and there is an intercept component coming in here itself. Okay, so here in this case, it says that the trend is not a significant value itself. Okay, so that means your choice of trend in the testing equation is also not a correct choice because the deterministic trend does not exist. Its p-value is okay 0.1731, which is less than 0.05. That means trend okay parameter in your testing equation is not a correct version to be tested for. Okay, and of course, okay, we didn't opted for a trend version in here in this case. Okay, I also simulated this series myself. Okay, so I know that there is no trend which has been there. Okay, but yes, of course, okay, you need to really go for this visual assessment of your data set before you really finalize your model for testing process. Okay, so still this is not an interpretable number. You should not be interpreting it right away. Again, change your equation. Okay, so you go to view, go to let me again go to graph itself. Okay, and come back to that equation. So trend, which you see perhaps in this case that there is a deterministic trend, okay, is really not been confirmed by the data set itself. Because if at this level the trend is moving upward, but for this level the trend is moving downward, okay, so what you perceive could be simply okay an issue in your visualization itself. Okay, so opting for a trend-based testing procedure for the unit root test is not a correct version. So what else you should be going for? Okay. Now, if you take what is the mean value of this entire series as opposed to the mean value here. Let me go to the graph. What is the mean value of this entire series hovering around? They will all be hovering around the value 0. Okay. But here on this random walk with the drift model, okay, the mean value is not hovering around 0. These mean values are hovering around okay some positive number. Okay, so in this case, okay, having a no intercept okay at all is also not an advisable choice to me. Okay, so you need to at least opt for an intercept based testing procedure for this series. Okay, for this series, okay, because they are all hovering around the value 0, okay, you would have chosen the none as the option in the testing equation, but here choosing none as the equation in the testing procedure is simply ruled out itself. Okay, so trend is not confirmed by your testing procedure. Okay, presence of or rather absence of intercept is also not validated looking at the graph itself. So the only choice which you have is okay to go for intercept based testing. Okay, so because the trend does not gets confirmed from your data set. Okay, so as I've been I quote it many a times. Okay, this is also a borrowed quote. Okay, your data analysis is not a science per se. Okay, it's not an exact science. Okay, you do have a science element, but it's not always okay that there is some element of the art as well. You need to master it. Okay, you need to by okay trial and error is okay the only thing by which you can master the data analysis itself. So here again, okay, simply the trend and intercept will not do. Okay, none option is also been ruled out because this equation is not hovering around the value 0. In this equation, okay, so in this series, these are all hovering around the value 0, so I have chosen none. But this is not hovering around the value 0, so I need to go for the intercept based procedure. Okay, so I opted for intercept and press OK. But even okay, I go for that. Okay, I now I have obtained my test equation results itself. So unlike this one, okay, I have okay, now if I go for unit root testing, I am opting for none. Okay, and press OK. Okay. So now you have two such okay results again coming up okay with you. This is what is finally to be reported and used for your analysis itself. Okay, this series is clearly a stationary series, this one, okay, because your p-value is less than 0.05, rejecting the null hypothesis which was saying that your series is a non-stationary series. So you reject that. That means you are accepting that this series happens to be a stationary series. Okay, just bear with me as far as I'm loosely using the word accepting and rejecting. Okay, you know by now. Okay, in hypothesis testing, you do not talk about acceptance. I rather talk about rejection or not rejection. Okay, you don't talk about the acceptance itself. Okay, but I'm using it loosely. Okay, regarding the interpretation. Okay, which we are having with respect to the data set itself. Okay, so here I'm rejecting the null and I'm saying my series is stationary. Here I'm accepting a null and I'm just interpreting that my series happens to be a non-stationary series, okay? Which was also been evident from my by visual okay, confirmation from my data set itself. Okay, so I'm happens to have, I need to keep, okay, my intercept in your equation itself. Okay, though this is not coming up as significant, but I should not remove this from my testing equation itself. Okay, so I'm keeping it in my testing equation. Okay, because the average value is not hovering around the zero. Okay, so you should be keeping an intercept in your model in your testing procedure itself. Okay? That's the one answer. Any question, any doubt to anyone at this stage? Any query to anyone? Okay, let's move forward. Now, we have already seen that this is my stationary series. This is my non-stationary series. Okay, so how can I make my non-stationary series into a stationary series itself? Okay, so again, when I'm going for the unit 2 test, okay, I can check, okay, whether my series, which is non-stationary at the level, okay, if I take a first difference of the series, okay, can that again result into a stationary series? Okay, that's the next question. So this series, this one is a non-stationary series. Okay, we are perfectly fine with my series 1 number, okay, because that series happens to be a stationary series, and I'm good to go as far as my further data analysis is concerned. But this series happens to be non-stationary series, and being a non-stationary series, unless I combine it with another series and go for its co-integration testing, okay, I cannot proceed further. So I need to go to the stationary series to proceed further for conducting the data analysis. Okay, so can I get my series as a stationary series if I go for the differencing itself? Okay, remember, if you had a trend, okay, then you would have to opt for detrending itself. Now detrending is automatically done by eviews, okay, or for most of the programs itself. Okay? But the only catch in that case is that the detrending which they do is only the linear detrending. If the series happens to be having a trend which is exponential or logarithmic or any other sort of a trend which is not a linear trend but non-linear trend itself, then in that case EVOs, okay, or for that matter many other software will not be doing the detrending. Okay, you need to do it manually as far as detrending of the series is concerned. Okay, so here I'm going for the first difference of the series. Okay, you want to have a feel of the data set, that how does a first difference data set will look like. Okay, we can also have that as well. So I can go for view, graph, and line graph. This is your data, which is the original data, my default data itself. If I take every observation and deduct a previous observation from that and compute what is referred as the difference series, okay, what does that look like? Okay, so I can also have a view of that itself. So I can have my option of differenced data as well. Okay, so my default or my raw data is the original data which I have. If I want to have a look at my difference data, okay, then the difference data look like something like this itself. Okay, so you have a difference data in this case, and this difference data, okay, what is again a nature of this difference data itself. Okay, so again need to go for the same exercise one more time. Okay, so I go to view, unit root test, standard unit root. Okay, at the level the series is non-stationary, which we confirm from the Phillips-Perron test as well. Okay, but at the first difference level, will the series will exhibit the stationarity itself? Okay, so answer is okay. Partly the answer is, by looking at the graph, you can make out that the different series exhibit a sort of a stationarity itself. Okay, so I go for first differencing. Okay, again I have a choice between these three. Okay, do you really think that there is an intercept in this particular series? Now the difference series, is there a, do you think that there is a trend in this particular difference series? If your answer is yes, okay, you can opt for intercept and trend. If your answer is no, there is no a trend in this kind of a series, so don't opt for the trend option. If you think that there is no intercept, they are all observations are hovering around the value 0, you can opt for none. But if these observations are varying from any positive or a negative number, any number other than 0, then you have to necessarily opt for the intercept itself. So you need to make a choice accordingly. Or one of the way out could be is you opt for trend and intercept as your first choice and see it yourself. Read the test equation, and if you find that a trend coefficient is coming up as significant, keep the trend in your data set. If the intercept coefficient is coming up as significantly different from 0, you keep that also in the equation itself. So I went for the trend and intercept, and I'm still doing a trial and error. I click OK, and I find that my trend is not a significant coefficient itself. So opting for trend in my equation is not a wise choice which I have made. So I must not be using the trend-based testing procedure. So again, go back to the testing procedure itself. And this time I am not choosing the trend. I am choosing for the intercept itself. So I went ahead. Your C, the intercept happens to exhibit some sort of a non-stationary, non-zero number. It's a significant number. So it is a statistically significant number. You cannot rule out intercept in your testing equation. So you must be keeping intercept in your testing procedure. It's always advisable to keep a constant in your equation. Unless there is a very strong theoretical mandate to use no intercept regression equation. Only in those cases, you can use the regression equation without an intercept. Otherwise, you always, as far as possible, it's always advisable that you keep the intercept in your regression equation, whether it is a testing regression equation for unit root, or whether it's a normal regression equation in your model building itself. As far as possible, you must be keeping the constant in your model, because that also helps, among many other things, that also helps in upholding the assumption number 5, neutrality of the error term, that the mean of the error term will be equal to 0. If you put constant in your model, the mean of the error term will always necessarily be equal to 0. But if you do not put constant in your regression equation, if the beta naught has not been there, then there is no way that you can ensure, I'm not saying it's always the case, but probably, this may be possible that the mean of the error term may not be exactly equal to 0. So for that purpose as well, always try to have a regression model which has an intercept in your model itself. So here, I will not be dropping intercept from my equation. I'm still keeping that. Now this is the final test results which you should be reporting, saying that your series happens to be first difference, normal series. If you take a first difference of the series becomes a stationary series. At the level, at the original value itself, the series is non-stationary series, which we were holding it again itself. So here the p-value is less than 0.05. That means you reject the null. What is the null? The d of these series, which tells you that the difference of the original series has a unit root. So different series has a unit root, or a different series is a non-stationary series, that's getting rejected. That means different series is a stationary series only. That's what is trying to make sense of it. However, for most purposes, simply a difference of the series does not have a direct economic interpretation. Hence, we don't generally go for the differencing, rather for ease of interpretation, and that's just for the ease of interpretation. When you have a series which is a non-stationary series, you compute their percentage change. You don't compute their okay, differencing, because it has an okay issue as far as the interpretation is concerned. Okay? The interpretation becomes complex. So what you actually do is, okay, when you are trying to test for the series, okay, you just don't take a difference data, but rather you have a choice here. You can take the raw data. The raw data looks like non-stationary. You have a difference data as well, but you also have a choice of percentage change. Okay, the percentage change, okay, data set is also been, okay. You can have a view here. Okay, you also have a log difference, which is also okay, it gives you the attributes of the data set itself. Okay, so there are a couple of jumps which have been there, okay, and so there are not too many jumps. Okay, so probably that is a part and parcel of your test results itself. Okay, so there are so many jumps which have been there. Okay, so there could be certain okay structural breaks in your data set which you can need to account for while analyzing this kind of a series. So please, okay, the idea of at this level was okay that you please do understand that whenever you have been trying to report the results of the unit 2 test, which are your stationarity test itself, okay, then just don't go and report all test results. Okay, we're having so many test results with you. It's a Philip Perron, okay, DF, ADF, another. Okay, so there is no point in reporting that. Okay, that should be dependent upon whether you recognize the presence or absence of serial correlation in your data set. Okay, or the heteroskedasticity in your data set. Okay, that should be the factors to be considered for choice of the test itself. So if you are clear about that itself, okay, only report those tests which are confirmed. If you have, for example, okay, sample size is relatively low, okay, you report for the decay Fuller GLS test, okay, where the power of the test is slightly better for small samples data set itself. Okay? That's the first aspect. Second aspect is, even if you have chosen okay a particular test, which option you need to select here, okay, you should also be mindful about that choice itself. Okay, it's not that okay probably you report the results of 4 tests, DF, okay, ADF, KPSS, Philip Perron, 4 test results are being reported along with okay a test equation which has an intercept, test equation which has a trend and intercept, test equation which has none, all the 3 options. So 4 tests and with 3 options. Okay, so 4 into 3. Okay, so that means 12 okay statistics you are having and you are reporting that. Okay, that actually shows that you don't know about the stationarity okay concept itself. So don't do like that itself. Okay, your choice here should also be a conscious choice, which one you need to select, and the choice of test should also be a conscious choice, that which one you should be selecting as well. Okay, this will be okay needed when you encounter a non-stationary series at the level itself. If at the level the series happens to be stationary, that's a perfectly fine, and you can go ahead with that itself. Okay, so that was one aspect. Okay. Any question, any doubt at this stage to anyone? Any issue, any question?
So, like you calculated it from the data which was non-stationary, right? Like this log difference and
Yes. This
so
was
how can we
non-stationary.
like in one test it was like stationary, it was looked like stationary. How can it be possible then? Because even this shock, like this shock represent that it was non-stationary.
The series was non-stationary. At the level itself, the series is non-stationary. To difference the series, okay, remember I was saying that when you difference a series, you can make a non-stationary series as a stationary series. So here I have taken a different series, and the series comes up as a stationary series.
Okay.
Okay, it's only after a difference that series becomes stationary. Otherwise, as of now, okay, at the level itself, with all your original data, the raw data, the series was a non-stationary series. Okay.
Okay, sir.
Any other query? Any other question to anyone? Okay, now let's move ahead and analyze these series in terms of their attributes, which are correlogram. Okay, so I go to my series and I go for correlogram. I go for the default itself, it's a level, and leg selection is automatic. I press OK here. Okay. Remember, this series was a stationary series. Okay, now I have a non-stationary series. I go to view, correlogram, etc. default. Now you can look at the basic difference between these autocorrelations as well. Okay, so this series is a stationary series. This series is a non-stationary series. Okay? So your stationary series have all your autocorrelations, correlation with itself. Okay, that's what is referred as autocorrelation, and correlations again with itself. Okay? But while controlling for any intermediate value, that is what is your partial correlations itself. So these correlations and partial correlation, okay, they are all non-significant here. Okay, so they do not have any significance level. So if your series happens to be a stationary series, okay, you've drawn your sample from okay, a stochastic process only, so you have a realization from of a stochastic process, then okay, that process happens to be a stationary process, then in that case you will be finding that your autocorrelation graphs, okay, they are all the observation happens to be not significant. That means they are all these correlations happens to be okay, not different from zero, and hence okay, there is no results. Okay, which there is no connection of today's observation with yesterday's observation itself. Okay? So what this the correlogram is also telling you, it's simply telling you that that there is that today's observation, today's data point is not affected by the previous observation itself. Okay? In your understanding, okay, with the example which I was continuing, okay, if I draw if I throw a dice and read a number from 1 to 6 from the dice itself, if I do this, okay, at time point 5, okay, I've drawn my data, okay, which is coming from rolling of a dice. So observation which is on 6 and 5, suppose this happens to be 6 o'clock and 1 minute, 6 o'clock and 2 minutes, 6 o'clock 3 minutes, 6 o'clock 4 minutes, 6 o'clock 5 minutes. So anything which you have been reading on 6 o'clock 5th minute, okay, that has nothing to do with what you have actually got in the 4th minute or in the 3rd minute or in the 2nd minute. It's totally independent of each other. Okay, so if you have this kind of a okay independent okay, events which is resulting in your data set, then the series happens to be a stationary series, okay, where there is a complete independence. You throw a dice, okay, the number which will be there on the dice itself, that has nothing to do with what was the number which appeared here, okay, in the previous time point, okay, yesterday, and that is also independent of what they will be getting it in the next trial, okay, in the next data point itself. It's totally independent. If that happens, all your correlation and partial autocorrelation will happens to be not statistically significantly different from zero. That means their p-value will be greater than your benchmark itself. But if it happens to be a non-stationary series, okay, not in always cases, in all the cases, but at least in some of these okay different attributes, if it is something which is not following your stationarity, something which is not following your okay, the complete independence, then in that case correlogram tells you something more. So these observations are not statistically significantly different from zero. Okay? They are okay, sorry, they are actually statistically significantly different from zero itself. All your p-values are less than 0.05, the cutoff. So that means the correlation which you are getting is a non-zero correlation. It's a high correlation, and you are getting this kind of a data set itself. So correlogram also tells you about the nature of the relationship between the variables itself. Okay. So you have okay, this as a correlogram. Now this is a correlogram of a stationary series, which is like a perfect white noise. Okay. So you have a correlogram here, but this is one such correlogram which shows here. I'm showing you a few more correlogram itself. You have correlogram here. This is another correlogram which is having a trend. Okay, so this didn't had a trend, but here it is having a trend. So when you are testing for this series for unit root, you must select with the trend option. Okay? Then you also have random walk without drift. Again, you have a similar correlogram. One jump here and something like this. You have MA series. Just like this one. You have something like this one. So all the series except your white noise series, the series one which you had, this one, okay, is showing you some significant correlation coefficient along your time series itself. Okay? So these are non-zero correlations which has been observed here. Okay, in your MA series, it was something like different. Okay, one increase here. So there was one increase here, and the rest of the values were almost zero. Here it's an opposite, but correlation, autocorrelation, they were having all significant itself. So in the case of another series, which is moving average series, the autocorrelation is showing you some increase, but then okay, this happens to be okay a non-zero correlations itself. If you go for the sign, okay, something you can show it here. This one and this one. So there's a one jump here, okay, and these are all reducing very gradually. Here, there is one jump in autocorrelation, but this is reducing again exponentially itself. So you have a different kind of graph of or what is referred as a correlogram of your series is okay, which again tell you some more about your data set. These correlogram tells you about that how much is the memory in your data set. Okay, what do I mean by memory? The memory means that okay, how much okay the previous observation in your time series is effective is affecting the successive data points in the time series itself. Okay? So it tells you some more about that itself. Okay? What is the q stats, what is the p-value? We also have something on that as well, okay, which can also be quite useful for that perspective. I have correlogram, okay, so which tells you about the correlation function and autocorrelation functions. Okay, so you have sorry. Okay. When you generate a correlogram, you get something like this, which has AC, which is autocorrelation, and PAC, Q stats and p-value. What is the difference between AC and PAC? Okay, so AC talks about that there is total effect, while PAC talks about only the exclusive effect itself. So if you have an observation today and you have an observation yesterday and a day before yesterday, so what the partial autocorrelation talks about is day before yesterday's observation affects today's observation directly. Okay, not through the channel that the day before yesterday's observation affects yesterday's observation, and then from yesterday's observation it affects today's observation. Okay, if you want to take that, then that will take into consideration in your autocorrelation function itself, which include the direct effect as well as the indirect effect, which is from yt minus 2 affecting yt minus 1 and yt minus 1 affecting yt. Okay, so the partial autocorrelation talks about the direct effect, while the autocorrelation talks about direct as well as indirect effect of the previous observation on successive observations itself. Okay, so that is also been interpreted from your correlograms. Okay. So autocorrelation is simply a correlation between your observation xt and with a certain lag, h lag, forward or backward itself. While partial autocorrelation talks about correlation between xt and t plus h. So, okay, that is till here we are the same, but after removing any linear relationship of all observation that fall between the two lag interval itself. Okay. So direct PAC talks about that how much this will affect this directly without getting this into the computation, while AC talks about in both the effect, direct effect or indirect effect, which has been by t minus 2 affecting t minus 1, and then it's affecting t as well. Okay. Mathematically, you can derive it from the formulation itself. For correlation, okay, that's not really a big deal. Okay, it's a same correlation formula which is you use it for computing Carr-Pearson coefficient of correlation is also been used here. But PAC formulation, partial autocorrelation, okay, needs some more adjustment to compute those values. Okay. And your Q statistics, okay, which has been also computed from the data set itself, okay, that is referred as Jung box Q statistics. And there the null hypothesis is that all your autocorrelations, okay, are equal to 0. Okay, remember it's a test of autocorrelation, it's not a test of partial autocorrelation. The test of autocorrelation that all the lag values for which you have been testing it, okay, they simultaneously happens to be equal to 0. Okay, so that is considered in the Q statistics, and p value is okay, as interpreting that on. Okay, so if it is 0.024 or 0.026, that means p value is less than 0.05. That means you need to reject the null hypothesis. And what the null hypothesis was saying, the null hypothesis was saying that this observation from 0.729 to minus 0.069, okay, all these observation happens to be okay, jointly put together equal to 0. But these are not necessarily equal to 0. At least one of them is a non-zero number. But we know it for sure. If you look at the first observation, it's a non-zero correlation. Rest of it is falling into the zero trap, zero bound, but the first one is a non-zero, and hence, okay, you are rejecting a null hypothesis for this observation as well. So that's how you can make okay interpretation of your correlogram. So, correlogram has a lot of implication in the modeling itself, but it's a very crude way of interpreting. If it is a very simple model, okay, you can make out something from your correlogram. But if it is not such a simple model, okay, then your task is that you refer to a procedure called the Jung box talk. Okay, what's been referred there? One second. So we have a procedure for the ARIMA forecasting. Okay, that's where you need to okay use it for the forecasting purposes. Your correlogram is helpful for simple models, but for complicated models, which is ARIMA modeling, okay, this doesn't have okay all the applications.
Sir, I have a question for correlogram. Can I
Box,
ask now or later?
sorry.
I have a question about correlogram.
Yes.
For first lag, what will be the PAC? Yeah. For
For
two,
lag 1, the PAC and AC will always be equal to 1 because there is no indirect effect. All the effect is a direct effect. So there's no the difference which we'll be having in PAC and AC for lag value equal to 1. Okay, PAC and AC will only be different when you have a lag value other than 1.
more
For
than
2, 3, 4, 5, okay, you will always be having a difference between the two numbers. But for lag 1, okay, with these two numbers, PAC and AC will always be equal to 1 and the same one.
okay. Thanks.
Yeah. Any other question? Any other doubt to anyone? Okay, then, okay, I think, okay, that was the time which I had, okay. I'm just recapping what I have discussed so far in the 2 day sessions. So I talked about, okay, what is the basic nature of a time series and how does time series differ from a cross-sectional data set and why you should be more, okay, concerned about dealing with the time series data because the time series data set, okay, they generally suffers from the problem of autocorrelation. So you need to account for that. And your time series data set, okay, should also be subject to the test of stationarity, because if you have non-stationary data set, okay, then in that case, you might, okay, fall into the trap of what is referred as spurious regression results. Okay, so you must not be running a regression on non-stationary data set. You convert them into stationary data set and then you run a regression. That's one solution. But okay, you should be having stationary series on which you run a regression. This rule has only one exception. If your series happens to be non-stationary, but then they are referred as co-integrated series, only then you can run a regression on non-stationary series. Otherwise, you should always be running a regression on stationary series. Okay. Then I also talked about, okay, how you check for the stationarity, how you opt for the various options which you have been having generally in the testing procedure, and these options must not be taken default. Okay, you should be conscious about what you are choosing, okay, as far as your test equation is concerned, and how you interpret the results of the testing procedure for these okay, unit 2 tests or stationarity tests, etc. Okay, that's in a nutshell what I talked about in the 2 day session itself. Okay. So still any question, any doubt, or we can wind up for the
Unfortunately, sir, we don't have more time. Otherwise, we would have loved to learn prediction of future values based on the equations derived. How future values can be predicted using
We do
those.
have, okay, ARIMA forecasting in EDU that solves it, okay, automates the procedure itself. So you have in your I think equation itself. Need to take some series, okay, which is, yeah, I have a series here. Okay, I can go for prop and automatic ARIMA forecasting is what you can opt for, and you can select the model which is a better model to be used. So here it is ARMA 00 model is a better model. So you could be using, okay, some other model. If in your data set, you can use this box Jenkins. Sorry, this is DRM. So instead of DRM, I take. Okay, yeah, that was the best model. Okay, you differentiate and then do the ARIMA forecasting. You know, for that. So that testing procedure can also tell you about what is the best model to select for ARIMA purposes, okay, and how you can forecast it. It's the best. Okay. It's a different series, okay, which is to be forecasted, and the better model is, okay, 00 model, no AR term, no MA terms, etc. Okay. That also makes it quite simple to move ahead with some of these softwares. Okay, but yes, of course, that do require some more amount of time for doing that itself.
Thanks, sir.
I think we don't have any more questions, Narayan sir. So with your permission, can I wind up the session? Any questions from any participant? Sir, am I audible?
Yes, yes, ma'am, you are audible.
So I think there are no questions. Really, Dr. Narayan, really thankful to you. What I have been really knowing is definitely that time series is one of the specific way how we analyze the sequence of data points that are being collected over a period of time. In a very nutshell, you have tried to explain the different aspects of time series. And I'm really thankful to you, sir, for accepting our invite to be the resource person, especially on time series. I just want to share with all the participants that sir has always been gracious enough. I have been telling a lot about it, but really sir has been gracious enough to always accept our invite and be there to share his knowledge. And as a friend, जितना मैं जानती हूँ, really he's a gem of a person, always ready to help us in any kind of a research problem that we as friends are having. And really, sir, I'm really thankful to you for always being there for us using this platform. Thank you so much, Narayan sir, for the session today. And really, it was a very happy learning. That is what was there on behalf of the participants, the feedback we could detect. Thank you so much, sir, for joining the session.
Thank you, everyone. Thank you, the organizers, and thank you all the participants for these sessions. Okay, I hope I could be able to add some value to your existing understanding on time series.
No,
Thank you,
definitely.
everyone.
I can share with the participants that sir is always email away, and any kind of a issue that it is there, Narayan sir always responds to those queries, especially on email. So you're most welcome to share any kind of a problem on mail with him, and definitely he'll respond back to you. So as sir was saying that we needed more time with sir, definitely sir, we'll be ensuring next time that we are able to devote more time on this particular. Thank you, Narayan sir. With this, we conclude this particular session. We take a break of around 10 minutes, and then we join for the next session by Professor Statistical. Thank you, Narayan sir.
Thank you.
Thank you. A very good evening, sir.
Yes, Anjali.
Uh,
Anjali, are you able to hear me?
yes, sir. Sir, you're audible. I'm just trying to find, sir. आप दो से join करते हैं ना हमेशा? Yeah.
So I think we should give 5 minutes break to the people.
Yes, sir. Sir, I have already announced a break of around 10 minutes, sir. Join back in, I think it is 9:40 now, sir. Sorry, 6:40. We join at 6:50, sir. And we start with the session, sir. Thank you.
Okay.
Sir, आपके दोनों के दोनों जो हैं, both are co-host now, sir. कोई problem तो नहीं आएगी.
ठीक है. ठीक है.